Michael Faraday, you worthless sack of crap! Did you lie about the electric fields, Michael Faraday?
You don't have to answer that question.
I'll answer that question. You want answers?
I think I'm entitled to them.
You want answers?
I want the truth!
You can't handle the truth!
Order! Order!
Is this magic? Am I actually doing something right now? Am I just a drunk guy who should probably go home because he had way much to drink? No. What's actually going on here is science. Now, I know you're all familiar with electricity. Whether you pay the bill for it or not, every night when you get home, you go home and you turn off that light switch. Or, when you wake up in the morning and you try to drag yourself out of bed to go to a job that you hate, or a business class that you just cannot stand, you turn on that light switch and you get ready for the day. Anytime we speak about electricity, what we're really talking about is the motion and the movement of charged particles. But we can never see these charged particles. So we can never really understand the fields that surround them whenever they move. So for the most part, we can assume that this proton and electron are more like a sphere. So rather than just radiating outward radially from the center, these lines are actually radiating all directions, even some of them towards you. Now, looking back to our Van de Graaff, you can probably understand now that this, essentially, is just a big Texas-sized proton, or just a positively charged surface. Looking at these pieces of paper that surround it, you can see that they almost represent what we're seeing in this diagram right here. So essentially, what I'm allowed to do by placing these pieces of paper all around this sphere is generate electric fields that we can visualize. Shocking, right? You see, now we're getting somewhere. Let's take some time to familiarize ourselves with the rules and regulations provided by physics. Take this eraser, for example. When I hold it up in the air as high as I possibly can, up here, we have nothing but potential energy. But right before the eraser hits the table, the eraser is filled with nothing but kinetic energy all the way. Now, neglecting air resistance because it's stubborn, we can imagine that the relationship between the potential energy of the eraser and the kinetic energy of the eraser have to be give and take. When one is at its max, the other one has to be at its minimum, and vice versa. Now the same applies with particles in electric fields. You see, the work done by a force in an electric field acting on a particle moving within that field actually has to be equal to the decrease in energy in the field.
P.
P. Momentum.
That's right, momentum. See, Newton likes to define momentum in his second law. Not the first, doesn't mean it's not quite as important, but the second law, as the force of an object. It's equal to the rate of change of momentum. Momentum, that is. Now, just like any other aspect of science, particles and electric fields still have to obey to this law. So, when you have a particle moving through an electric field, its interactions with other particles and its interaction with the field itself causes it to lose momentum, or at least change momentum. However, looking at the particle, we find that some of this momentum just gets lost. It doesn't get transferred to any of the other particles it interacts with. It just seemingly disappears. We could accept that. We could go home and we could sleep well. Or we could try to face it for what it really is. What's actually happening is that momentum is getting lost in the electric field. The field itself is storing that momentum. Thus the reason why it's all conserved in the end.
You want answers?
We should ask you what your lines were.
I decrease in energy. No, I got that wrong. Crap.
Yeah.